Hello and welcome again to the Engineering Dynamics Course Companion. We're in class 21, continuing with kinetics of rigid bodies. Now we're going to do Newton's second law in translation and rotation, right? And plane motion. Yes, we are. As always, you could go down to the table of contents down in the description below and jump to the example. But let's start out with the bottom line up front. All right, we're going to do more on Newton's second law in rigid body motion, kinetics. It's often necessary to break apart an assembly into multiple parts and then apply Newton's second law to each of them. And this is also, you want to keep in mind that even though this is kinetics, sometimes the kinematics of rigid bodies that we covered in chapters 13 through 18, that can also play a part, right? The stuff on the right-hand side of F equals ma and the sum of the moments equals the effective moments, the stuff on the right-hand side, that acceleration, they still have all the different workings of the different parts that you might have from rigid body kinematics. So keep that in mind. We're not on an island in each of these topics. They're interconnected. All right, so here's the example. This is the one continuing from a previous example, but now we're going to add in the kinetics, right? So before this was a kinematics problem where we treated with velocity. That was first. That was velocity analysis. That was like let's see, what was it? We were in 14 right there, chapter 14, class 14. And then we used instantaneous center of rotation in class 15. And then class 16, we did acceleration, right? So now we're going to figure out, that was all kinematics describing the motion. Now we're going to see what's causing the motion right here. Okay, so we have 4 feet and 6 feet. Those are the lengths of these pieces. That's what we're given. We know that the thing weighs 100 pounds. At this instant, it's at 25 degrees right here. And we assume the wheels, the mass of the wheels are negligible and the pins are frictionless. Those are all important. We want to determine the translational and angular accelerations of the rod at this instant. I think we could say that they're starting from rest as well. I think we need to know that. So I jumped ahead and got the mass moment of inertia of the link right there. Once again, this is not a fixed point right here. This whole thing is translating and rotating. So that's what makes it different between the last class. So we got the mass moment of inertia. Make sure that we always careful here because we're in US units. So we had to divide the weight by 32.2. And we're treating this like a cylinder rod, so it's 1/12 mass times length squared. And then so we do an FBD and IBD of the two bodies right here. Boom. And we have the weight. That's the thing. That's really the impetus of this thing that's making the thing go down. We also have the reaction force at A, and we have a reaction force at B. Now, we're going to say that it's going to translate, it's going to accelerate going in that direction, or we're assuming it's going to the right. We'll just make that assumption. And then I'm pretty sure it's going to be going downwards at the center of gravity. And then there's also an angular acceleration going clockwise. Right here, right? So we take the sum of the moments, the effective moments, and let's take it about A. We could probably have taken it about B as well, but just bear in mind that a lot of times we want to try to get rid of one of the unknowns. And quite often it's going to be one of the reactions. So that's our strategies to take it about A. So let's see. We carefully go through and we say, well, this force right here due to B, right? So we feel like it's going to be the wall is pushing back against the thing at B. I had to be careful, like in some instances, B might actually separate from this wall if there was nothing that was forcing it to be on there. Or if it was it was in a slot, that force could be in the opposite direction. So just be mindful of that. So we take there's going to be that force times. We have to be careful that we either want to take the portion of the force that's perpendicular to this, or take the length. And in this case, we took the length, right? So we went ahead and said that this is the length right there. That's going to be the moment arm, and I'm just sketching on top of there to communicate. That's what that length times the sine is going to be, right? Yes, that's true. Right here. Wait, I drew it wrong. Right there. That's the length. Yes, the length right there. Because we're taking B right here, and we want the perpendicular distance, right? That's going to go past through A. All right. And then the weight right here, we have to, okay, so that's going to be like right here, right? So that's going to be that distance, but we want to actually have it be through this distance right here, right? So that's why that S, and then this is the angle right there. So that's going to be the cosine of theta. Yes. Okay. Right. So we want to pick this apart carefully as we're going through and look for these little potential mistakes. All right. And then on the right-hand side, so we have the spinning of this thing, and that spinning is going to be clockwise. And we're also going to have this mass times acceleration, mg, taking place. And I believe that this should probably have been in the opposite direction right here. But we'll proceed. And then we have mass here. Okay, so this is mass times the acceleration in the x direction. So that was going that way. So that was positive, right? And because it was, we were taking, and then we're taking this distance right there. So that's the LAB. See, I think this is a mistake right here. I think I found another mistake. That's just great. Because that really should be this distance right here, right? So that should be the same as I do over here. Now I have this one correct, where I have the mass times the acceleration in the y direction right there, and it's going to be times that that entire length, the LAB plus LBC divided by 2, and then times the cosine of that angle right there, and that's going to give me this distance right here, right? And that's okay. So let's keep going. We plot all those things in there, and we note that we have this unknown accelerations right here. Now we can't really plug in that L and a hat, the accelerations that we would like to, right? We can't do the same thing that we did in the previous class, because this thing is translating and rotating. They're not equal to, right? In this case right here, because it's translating, this times L over 2 does not equal the tangential, if you will, right? That's not true, because we have those other components that we have to in kinematics that we need to include. Now we also have, so this is equation 1, right? This is where we're stuck right there. We don't know this, we don't know this, we don't know this, and we don't know this. That's one of the reasons what makes this these problems more difficult, is there's lots of unknowns. But we're going to see that there's enough equations that are going to help us out. And then so we have the sum of the forces in the x direction. That's going to help us with FBX right there, and we know that the only thing that we care about was the force in the x direction right there. Is going to be equal to the mass times the acceleration of g in the x direction, right? Those are the only forces that are happening in the x direction. So that's probably why I selected this to be positive right here, because I drew this, I knew this and that had to be in the same direction as each other right here. So here is an equation, here's equation 2 that we can relate into there, right? Okay, so continuing on here, we do an acceleration diagram. That's going to help us get the kinematics to help to relate how some of these things are moving right here, right? So we know the acceleration of A must be over to the right, and acceleration of B must be down, but we don't know what they are yet. And we're going to need to relate the acceleration at the center of gravity. That's going to be something important to us. So I'm going to use the acceleration at A as going to be the reference to the thing. So we spin it about A, and so in the tangential direction, that's going to be the tangential acceleration that we would find. And here's where the angles are and the lengths that would take place. And what's good for us is I think we don't have any normal acceleration in this case because it doesn't have a velocity. It doesn't have angular velocity right here, right? So in the x direction, setting up these things, so that's, and because there's no velocity, that's why that's 0 right here. We could see that the acceleration at A right there and is going to be, that's completely in the x direction. Then we have the acceleration to the tangential right there, right? So that's going to be, and we're taking this guy right here, right? So we're relating A and B together, right? A and B, but at B, we know in the x direction it's going to be 0. So what that lets us do is have another equation, right? So that's a good thing. And then now we can set up the acceleration at the center of gravity, right? So we don't really get any benefit out of doing the y direction, I don't think. Okay, so here's the acceleration at the center of gravity for the thing. In the x direction, and once again, we're using the acceleration at A as the reference. And so now the and so we could plug in for this all of the different knowns that we have. Okay, so or we could set it up here. Okay, so here is the this right here. So that's what this guy is. Yes, and we're taking the sine of that angle. Let me see. Yes, yeah, because we want to get in the x direction. Yep, and that should be negative. Yes, it is negative. Okay, and we put in what we know, what we had from equation 3. We put this in here, and now we have the acceleration in the x direction related to alpha. That's good, and I think we have to do this again for the y direction. Okay, so we don't have the diagram that's on the previous slide, but we take a look at that. Let's come back up here and take a look at the y direction. Okay, so in the y direction here, we're going to take a look at this. That's what we want, and we're using the, okay, well, it's 0 in the at A. That's good. And in the y direction, this is going to be downwards, and we're going to be taking the cosine of that theta right there. Okay, so here it is. Yep. So we have 0 right here, and we have that cosine, and I think that negative should have stayed in there. We'll see in the next equation. Yes, we had it right, but maybe that negative should have still been in there. Yep. So we have this equation 5, right? So we could go back and we could take equations 1, 2, 4, and 5. We could put all of these things together, right? So that was equation 1, and there was 2, here's 4, and here's 5, right? So just summarizing what they were because they were back up on other slides previously. So sticking them all back in there, you can see that we have a number of these alphas right in there, right? So, and even, so you'll see that we have that that force of B right there in terms of AGX, but we also had what AGX was going to be, so that was where we were able to get put into this guy right here, right? So we put all of those in it, and we have alpha, and we're able to find what alpha is. Now that we have alpha, we can plug these back into the previous equations that we had. So like you could see, this is equation 4 right there. We're able to put that alpha back in. And here we're in equation 5. We're able to put the alpha back in, and we're able to find what those accelerations are going to be. And now we can take, and I think that was what we were trying to find, right? We were asked to find the acceleration of the center of gravity of the thing. So here's the magnitude, and then here's the direction. And you know it's going to be going down and to the left, and here is the angular acceleration. So there was a lot of stuff going on in this problem. So let's take, you can rewind backwards for this, but let's take a little cruise through this thing one more time, right? All right, so in summary, we got the moment of inertia. We draw the FBD. We start putting on the loads that we know, and then the loads that we don't know. We put in the motion that we expect at the center of gravity and the rotation, and we write the thing out for the effective moments, right? And when it came to the signs of things, I was a little suspicious about the thing in the x direction. But then when I got to this next step, I said, well, I know that the force must be pushing onto the thing, or I suspect that it is. So that's the direction of the mass times acceleration. So that's the direction the acceleration is going to be. And I set those up and I got an equation, right? So they got 2 equations so far, but there's a bunch of unknowns, right? So we wanted to get rid of those unknowns by taking other things that we know, which is going to be the kinematics, and set up those acceleration relationships and march through and find another equation for that at A, the acceleration at A, and we can then do the stuff at the center of gravity, and we can find a relationship for there. So there's another equation, and then finally we were able to get the acceleration in the y direction at the center of gravity and plug all those together to be able to find the things that we're ultimately out to get. So there's a lot of things, a lot of steps to be looking at here. But that's what I like, having more complicated examples. They make you think through and look through the process, and hopefully you've been able to follow what went on in this problem, and then you could take a look at other problems and kind of have the mindset as you start to approach them. And if you run up against a hurdle, if you run up against a barrier where you get stuck on a problem, you can navigate around by looking for other possible things that you know are taking place. And in this case, that's the kinematics that really helped us out. So for more examples, check out the Engineering Dynamics Course Companions Parts 1 and 2 right here. They're available from Morgan and Claypool Publishers, and you can go to them by going to the links below to go to the publisher. You can also get it from Amazon if you look it up. Do a search on the Engineering Dynamics Course Companion. And please consider subscribing to this channel. I will put up updates and new videos from time to time. So from Wormy and I, thank you very much for your time.